All right, so we're going to look at our last section, last part of the section for this week, which is 2.1 part 3. It's on what we call angular velocity. So this section is going to have a lot to do with conversions, okay? Converting one thing to another, kind of like we've been doing with degrees and radians, okay? Except there'll be some other conversions in there as well. So what angular velocity basically is, very simply, it's the speed of something spinning. Right? So if you look at a car and it has a tachometer in it, and it has RPMs, revolutions per minute, that's a speed. It's not linear speed. It's not like miles per hour. It's the speed of something spinning in a circle. How many revolutions is it making in 1 minute? And it's important to kind of understand, how do you convert, not just like degrees to radians, but how do we change like minutes to days? How do we change years to seconds, right? So we're going to go through a couple just basic conversions to try to see the process. And then from there, we're going to tie in some stuff with degrees, radians, and revolutions. But we'll start with some units that are probably more familiar to you. So let's just start with that. We're going to convert 4 days to seconds. Now, most basic conversions I would expect you to know. How many seconds in a minute, minutes in an hour, hours in a day, days in a year, inches in a foot, feet in a yard. Those kind of things you'd have to know. If it was something strange, like you need to know how many centimeters in an inch, that's a little bit of a different one. I would give you something like that. Okay, so the way that we're going to convert days into seconds is we're going to go 1 unit at a time. So we'll start at days, and then we're going to go the next unit smaller than a day. All right. So, Ben, if we're going to convert days to seconds, what's the next unit smaller than a day? An hour. Yep, we've got hours. So what we're going to try to do at this step is we want days to cancel out, and we're going to get it to hours. Okay, so Frankie, if I want days to cancel out, and you can think of it like this if you want, where would days have to go in the second fraction? In the top or in the bottom?
No, top. No, bottom.
Bottom. How come?
So we can take away all the days?
Yeah, well, if you have the same thing in the top and in the bottom of a fraction, in the multiplication, it cancels out. So we have days in the top. We're trying to get rid of days and turn it into hours first. So days will go in the bottom. Hours will go in the top. And now I need the conversion between days and hours. So Dominic, what's the connection between hours and days?
24.
What? Can you be more specific?
24 hours in a day.
24 hours in 1 day. Thank you. Good. Okay, so that's our first step. Now we're going to get smaller than a day. So Raymond, what's my next unit down from a day?
Hours.
I'm sorry, yeah, we did hours. What's the next unit down from hours?
Minutes.
Yeah, minutes. So now we're going to get minutes. So we want hours to disappear. James, where would hours go if we wanted to cancel out?
The bottom.
Hours would go in the bottom. Minutes would go in the top. And now we got to fill in the conversion. Hours to minutes. Colby, what's the conversion between hours and minutes?
60 minutes in an hour.
60 minutes, 1 hour. Okay, so now days is gone. Hours is gone. And if we stopped here, we'd be left with minutes. Okay, we're going to go one more step, smaller than minutes. So Lacey, what's my next unit down from a minute?
Seconds.
Seconds. Jacob, I want to get seconds. I want minutes to go away. where would it go?
On the top, the seconds on the top.
Yeah, seconds would be on the top, and what would be in the bottom?
The minutes.
The minutes. Now, minutes in the bottom, minutes in the top is gone. There are 60 seconds in 1 minute. Now we look back and we say, what's the only unit we have left? Seconds. So as far as writing down conversions, we're done. Now you multiply straight across. Not always, but a lot of times in the bottom, you're going to end up with ones. So there's nothing we have to do there. Sometimes there will be. It depends. But we're just going to multiply straight across. So we've got 4 times 24. And then 60 times 60 is 3,600. I just did that part in my head. So that's 345,600 seconds. And that basic idea of how we just change days into seconds, we can do that with any minutes. The key is you just have to look at where you want to put the label for it to cancel, and then fill in the conversion. Okay. All right, so this is just a single number, 4. The next one is going to be a little bit different. Okay, we're going to use the same approach, but it's not a single number. It's going to be a speed. A speed, well, it's a single number, but it has 2 units. It has a distance unit and it has a time unit. So this particular problem says 14 feet per second. So feet per second. That's what makes it a speed. Distance per time. All right, so when you see 14 feet per second, that means you're traveling 14 feet in how many seconds? Done? 1. That's 14 feet in 1 second. So now it's like we're doing 2 problems. We have to change feet to miles, and we have to change seconds to hours. It doesn't matter which one we do first. Let's do the feet to miles first. Okay, that's one step. Even if you don't know the conversion between feet and miles, you should know where feet has to go to cancel out. We want feet to go away. Jaden, where does feet have to go to cancel out? It's got to go in the bottom. Feet in the bottom, miles in the top. Now we need to know the conversion. How many feet in 1 mile? Yep.
5,280.
Yeah, some random number, right? 5,280. Not like the metric system where everything is based on power of 10. That's a little easier to remember. But there are 5,280 feet in 1 mile. Now you have miles per second. We want miles per hour. So, the miles unit is done. We're not going to touch that for the rest of the problem. But how about seconds? What about Mateo? What's my next unit up from a second? Getting towards an hour.
Minute.
A minute. So if you wanted to get rid of seconds and bump it up to minutes, where would seconds have to go?
The top.
Yeah, it would have to go in the top. Seconds in the top, minutes in the bottom. 60 seconds in 1 minute. Seconds in the top, seconds in the bottom, cancels. Now you've got miles per minute. Okay, we gotta go one more step. Katrina, my next unit up from a minute, and the final unit I want in the problem is hours. Where would minutes go to cancel out? Top, hours in the bottom, 60 minutes, 1 hour. And now go back and look at your units. Miles per hour. Okay, so now all that's left is to multiply straight across. You could reduce, but that just gives you a chance to mess something up. So let's let the calculator reduce it for us. So you got 14 times 60 times 60, which is 3,600. So that's the top. And now I'm going to divide that by 1, 5280, 1, 1. So just divide it by 5,280. 5280. So 14 feet per second is about 9.55 miles per hour. And that's one you can write as miles/hour, or you could put mph for miles per hour. You might also see it that way. Okay, any question on that one? All right, so this is an example of what we call linear speed. Linear means it measures the distance from point A to point B, like something moving in a straight line. Okay? This doesn't measure how fast something is spinning. That's different. How fast something is spinning, that's called angular speed. Okay? But this is linear speed. And this is kind of the generic formula for linear speed. You always take distance and divide by time. Okay. Some people learn it this way. Distance equals rate times time. Has anybody ever seen the formula this way? D equals RT. I'm just using the same letters our book used. All right, so keep that formula in mind. Velocity, or, I meant to write speed here. Velocity just means speed, how fast. Writing a word and then putting the same word next to it in parentheses doesn't really help much. All different kinds of units you can have for linear speed. Miles per hour, that's pretty common in like the US. Kilometers per hour, that's what you'd see in a lot of European countries. Feet per second, that's another unit you could use. But now, let's take a look at angular speed. So, it's still a speed, which means it's going to have a time unit. Could be hours, could be minutes, could be seconds, could be days, but it still has a time unit. But the difference is the distance unit. When you're talking about angular speed, the distance part, it can't be measured in feet or inches or centimeters. That's for measuring things that are straight. Angular is for things that are spinning. So the way we can measure the speed of something spinning, we can measure it in revolutions, we can measure the distance in radians, or we can measure it in degrees. Those are really the three ways we can do it. The time unit could be anything. Radians per hour, radians per day, radians per minute. But these are the three units that you can use to measure something spinning. A revolution, a radian, or a degree. They all measure circular motion. So let's take a look at this diagram. Okay, what I have here is a circle. And I have three different colored dots on it. I've got a black one in the center, a red one, a little bit further out, and then I've got a blue one all the way on the outside. So what I'm going to do is I'm going to take the circle and I'm going to do this. What did I just do? All the dots just made one what? Yep.
360-degree rotation.
Yeah, they all just made one revolution. Now, which dot traveled the farthest? Yep. Which one?
The blue one?
Yeah, the blue one. Okay, the blue one traveled the farthest, and the black one traveled the least. It was right in the middle. It's like it didn't even move. Now, if you compare, watch it again, the time it takes the black one, the time it takes the red one, and the time it makes the blue one to make one revolution. How do the times compare? For the black one, the red one, and the blue one to all make a revolution. Yeah. Tom?
They're the same.
They're the same. Okay, so think about that for a second. You told me the blue one was traveling the farthest. But they all made one revolution in the same amount of time. So, what does that mean? If something is traveling further than something else in the same amount of time, what does that mean about it? It went further in the same amount of time as something else. It means it would have to be what? Yep.
Going faster.
Going faster. And that's where the confusing part comes in with angular velocity. If you try to measure it the way we think of linear velocity, every single point on this circle moving out from the center is going at a different speed because it's traveling further. Something travels further in the same time, it has to be going faster. So we don't want to try to describe angular speed that way. It gets confusing. If we describe angular speed using revolutions, then we can say all of these dots made one revolution in 5 seconds. All of them. They all traveled at a speed of one revolution per 5 seconds. Right? That's easier to describe. So when our book asks for angular speed, the default that I want you to use is radians per second. So sometimes you might see a problem that says find angular velocity, and they don't tell you what to do. So should I use seconds? Should I use minutes? What should I use? I'm telling you, if they don't say anything, stick with radians per second. If they ask you to do something else, like they say find the speed of the object in revolutions per minute, then do what they're asking. So we'll practice a few more conversions. The particular one, sometimes people have a little trouble with, is converting angular to linear. You can convert between the two speeds. And I'm going to show you how. This first one is just a conversion from an angular speed to a different type of angular speed. Revolutions measures angular speed. Radians measures angular speed. So we're just changing it. It's like changing feet per second to miles per hour. You're still measuring the same type of thing. You're just going to use different units. So let's write down what this means. 4,000 revolutions in 1 minute. Jody, is there any unit that we're given that we don't have to mess with in this one? Minutes. We don't have to mess with minutes. They gave us something in minutes. They want the final answer in minutes. So leave minutes alone. What they don't want is revolutions. We have to convert revolutions to radians. Now, even if you don't know how many radians in a revolution, which we learned, but if you don't remember it, we should at least know where revolutions has to go. So Pete, where does revolutions have to go to cancel out? Top or bottom?
Bottom.
Yeah, very good. So we're going to put revolutions in the bottom. We're going to put radians in the top. Revolutions in the bottom cancels with what's in the top. But now I need the conversion. Does anybody remember how many radians in one revolution? Yep. That's part of it. Yep. 2 pi. So there are 2 pi radians in one revolution. And now we just multiply. In fact, we don't want a decimal. This one is easy. 4,000 times 2 pi is 8,000 pi radians per minute. If they want a decimal, then I'm going to need my calculator. 8,000 pi is about 25,132.74. So that's the answer if they wanted it as a decimal. Okay, any question on that one? So I think for the next one, it kind of helps to visualize like what would it even mean to convert between angular and linear speed? Well, imagine that you were swinging something, right? You got something you could spin on a circle. So this is making a certain number of revolutions per minute, right? Maybe 60. And then all of a sudden, I take it and I let it go, and I don't get it. Right? I let it go. When I let it go, it's going to take off in a straight line. All of a sudden. It's not going to be able to be spinning in a circle anymore because I'm letting it go. When I let it go and it takes off in a straight line, it's instantly going from angular speed to linear speed. It's going straight. So that's an example of how something could convert from angular to linear. Same idea. If you had like a car tire and you had it on like a machine to balance it, it spins it real fast to balance it. Well, imagine all of a sudden, for some reason, that tire fell off the machine and it hit the ground. If the tire is spinning really fast, all of a sudden it's going to go from just spinning in place, it's going to hit the ground, it's going to take off straight, right, really fast. So that would be an example from going angular right into linear. So let's look at this example. So it says a child is using a 2-foot rope. There's a rock tied on it, and they're spinning it at 180 revolutions per minute. Find the linear speed of the rock in miles per hour. So basically that would mean if he was spinning it and all of a sudden let it go, how fast would it go? Of course, if you let it go and the rock went straight up, it would slow down because of gravity. But if you let it go sideways, it wouldn't slow down. It would just fall to the ground slowly. We don't really need the diagram, but we've got it in case we need it. All right, so what we're going to do, we're going to start with the speed that they give me, and I'm gonna write a series of fractions until I finally end up with what they tell me to. MPH means miles per hour. Alright, so Ava, what's the speed that they give me to start this problem off?
180
Yeah, 180.
radius per mile, radius per minute. I don't remember.
Yeah, what does RPM stand for again? That's an abbreviation you might see on like different power tools or something. If it says RPMs, what does that usually refer to? Yeah, Jane?
Rotation.
Yeah, rotation or revolutions. Okay, so RPM always stands for revolutions per minute. Okay. Just like MPH always stands for miles per hour. It's just one of those abbreviations, they'll shorten it to 3 letters. Alright. So, we've got 180 revolutions in 1 minute. Alright, so Vivian, looking at the time unit, let's start with that. The time unit that they gave me to start with is what?
Per minute.
Minutes. And the time unit that I want to get in the end is what?
Per hour.
Hours. So I don't have the right time unit. Let's take care of that first. So let's get rid of minutes and turn it to hours. All right, so Dawn, if I wanted to convert minutes to hours, how would I do it?
Multiply by 60.
Okay, and what unit would go in the top?
60 minutes.
60 minutes. And what's in the bottom?
1 hour.
Perfect. 1 hour. So at this point now we have revolutions per hour. All right. Revolutions is how they're measuring the distance. But what unit do we want in the final answer for distance? We don't want revolutions. Yep. Is that what they said? Yeah, they want miles. So we have to get revolutions to miles. Okay. So what we want to think about now is, think about this circle. That's a revolution, okay, what I just drew. I need to find out how big that revolution is. So what's another name for a revolution? If you think about it in terms of a shape, like the circular shape, it's the what? It's the circumference. So, I can't go quite to miles yet because the problem has feet. But if I can at least get to feet, then changing feet to miles is easy. You just have to use a conversion. So what I'm going to try to do is figure out the circumference of this circle. Once I know that, that'll tell me how many feet are in 1 revolution. So the conversion between feet and revolutions is not a standard conversion. It's not like saying how many minutes in an hour, how many seconds in a minute, how many hours in a day. Those stay the same. They never change. But how many feet are in a revolution? Well, it depends how big of a revolution you're making. Is it a small revolution or is it a big revolution? It all has to do with the circumference. So let's find the circumference of this circle. It's 2 pi times 2. And Sean, if I simplify that, but leave my answer as a multiple of pi, what do I have? What's 2 pi times 2? Yeah, 4 pi. So there are 4 pi feet in a circumference. 4 pi feet in 1 revolution. So let's write that down. Revolutions is gonna go in the bottom. Feet goes in the top. There are 4 pi feet in 1 revolution. In this problem. In another problem, it might be different. It depends on how big of a circle. Now, the important thing, though, we've done is we've jumped to linear speed. We've gotten rid of revolutions. That was angular. Now we're in linear. Now, from here, we just have to change feet to whatever they want us to have. They want us to have miles. So, again, how do I change feet to miles? What would go in the top? Okay, and what would go in the bottom? Feet. And can somebody fill in that conversion for me? How many feet in a mile? Yeah. 5,280. Feet and feet. Okay, so this conversion, standard, never changes. It's always 60 minutes in an hour. This conversion, very standard, never changes. It's always 5,280 feet in a mile. This conversion is different. Different in every problem. You have to use the circumference formula to figure that one out. Any questions on that before we multiply? Okay, so let's multiply straight across. Okay, and I'll show you how you can do this one all in one step. So let's do in parentheses 180 times 60 times 4 pi. Do I need to do times 1? No, that part doesn't matter. Divided by, in parentheses, 1, 1, 1. I don't need any of those. 5,280. So, if this was the situation, okay, someone's spinning a rock on a 2-foot rope, and they let it go, the speed that it would go in miles per hour would be about 25.7 miles per hour. Okay, so every problem in this section is all based off these fractions. I'm just writing down conversions. That's how we're doing it. Yeah.
To write down our answer, can we say either MPH or
Yeah, for miles per hour, you could write MPH, same with revolutions per minute. You could put RPMs. Yep. Those two are common units to write that way. Right, other questions on this one? All right, so let's this one I think was one that was in the homework. Yeah, 97. So let's take a look at this one together. And then you won't have to do this one for homework. Okay. It's a word problem, but I took out the important things from it. Let's make sure we know what these actually stand for. Frankie, what do you think the R stands for? Frankie? Frankie, hi. What do you think the R stands for here? This R. What is that? them out, Tom? You have them out?
The radius.
Yeah. R is gonna stand for, that's my radius. Okay, Raymond, what about the T? Well, what does T equal? What does it say? T equals
Oh, seconds.
seconds. What do you, seconds is used to measure what kind of thing? Time. Alright, so that's time. And theta. What is that Greek letter always used for? That's an angle. So it looks like they're starting me off with angular speed. They're telling me a distance, they're giving me a time, and I can write the angular speed. So it says find the angular speed and the linear speed. Now, I wrote it exactly the way the book did. They didn't say what units to use. They just said find angular speed. That's a very vague question. So, if our book asked us to find angular speed, use radians per second. That's what we're going to use. All right. So remember, speed, whether it's angular or linear, is always distance over time. Okay, distance over time. Colby, what number here represents moving a certain amount of distance?
The angle.
Exactly, the angle. You're moving 1/3 of a radian. It's not linear, it's not straight, it's in a curve. It's on a circle. So that's my distance. So 1/3 of a radian. And Jaden, what's my time here? 20 seconds. Now, this is radians per second. That's the unit I asked you to use, but that's kind of a weird way to write angular speed. That's like telling you I was traveling 200 miles per 4 hour. When you tell someone a speed, what number do you usually put in the fraction? Yeah? 1. You usually want a 1. So you could understand, well, instead of telling you I was going 200 miles per 4 hour, that means I was going 50 miles per 1 hour. All right? So let's see if we can fix this so we don't have a 20 in the bottom, but we have a 1. So then it says radians per second. What could you multiply the top and the bottom by? You got to use the same number. So as an example, if I said to you I was going 200 miles per 4 hour, how fast does that really mean I was going? I would multiply the top and bottom by 1/4. And what that does is it turns the bottom into a 1. And it turns the top, 1/4 of 200 is 50. So 50 miles per hour. So what could I do here? Yeah.
120.
Yeah, multiply top and bottom by 120. 1/20th times 20 is going to give me 1 second, just like I had over there. And 1/20th times 1/3, just think of it like this. 1/20th times 1/3. Just multiply straight across the fraction. That's 1/60. So there's your speed. It's 1/60th of a radian per second. You can make 1/60th a decimal if you wanted, but we can leave it like that. Okay, any question on that part? Yeah.
bottom by 3 and have it be 1 radians over 60 seconds, or do you want to have the second after 1?
You generally want, when you're telling someone a speed, you really want the number in the bottom to be a 1. Kind of the same reason why if you told me how to convert feet to inches, you'd probably tell me 12 inches in 1 foot. You could tell me 24 inches in 2 feet, but I'm guessing you probably wouldn't, because 1 is just an easier number to think about. All right, and now let's finish up with linear speed. They didn't specify, so just to keep it as easy as we can, let's find the linear speed in centimeters per second. Yeah.
I just wanted to go back to that for a sec. Wouldn't it, I think, what they're saying is, wouldn't it be easier to swap where the 1 is, so you have 60 seconds, 1 radian?
You mean multiply top and bottom by 60?
Yeah.
So 1 radian in 60 seconds? You could write it that way.
Wouldn't it be easier that way than having a fraction at the top?
It depends on what they're looking for. It certainly, you could do it that way. There's nothing wrong with that. So what he's saying is write this, 60 or 1 radian in 60 seconds. Well, it'd kind of be like saying I traveled 5,000 miles in 60 hours.
Isn't that just 1 radian in 1 minute? So it's 1 over 1. I don't.
If we converted to minutes, yes, you could change that 1 radian per minute. You could, yep. So since they said to leave it in radians per second, we'll leave it in seconds, but absolutely you could change that to minutes and you'd be correct. But you don't have to do that in this problem. All right, so now let's take our speed that we have and let's see if we can get it to be a linear speed. So we have 1/60th of a radian. And again, if we were using minutes, I would put, I could use minutes, but I'm going to stick with seconds because they said to use seconds. So what's nice about that is we don't have to mess with the timing. They gave us seconds, they want seconds. So we don't have to change that. What we do have to do is get rid of radians and change it to centimeters. For now, don't even worry about the numbers. Cassidy, where would radians go?
On the bottom.
Yep, we'll go on the bottom. Centimeters is going to go on the top. So I'm going to leave that there. You know what? We'll do one more thing. Actually, well, you can leave it like that, I guess. Doesn't matter. Now, to convert centimeters to radians, all right? First, we're going to have to think about how many centimeters in a revolution. We can't really get how many centimeters in a radian right away, but we can get how many centimeters in a revolution. That's easy. A revolution is really what on a circle? It's a circumference. So anytime that you want to change angular to linear, you always have to use the circumference formula. Circumference is 2 pi r. Okay. So in our case, hopefully I wrote down a radius up here. Good, I did. The radius was 5. 2 pi times 5 is 10 pi. So I know that there are 10 pi centimeters in 1 revolution. Now I have radians here, but that's okay. It's not that far off. How many radians in 1 revolution? I think I asked that earlier. Yeah, 80, 2 pi. So using the circumference formula, we know that there are 10 pi centimeters in a revolution, and we know that there are 2 pi radians in a revolution. This part is a standard conversion that never changes. There are always 2 pi radians in a revolution. So, look at what we've written right here. That conversion would help us to finish that off. We know that there are 10 pi centimeters in 2 pi radians. And we could cancel the pi's out. All right, and I'm going to use my calculator to do that because it has some fractions in it. So I've got 1/60th times 10. So let's do 1/60th times 10. Okay, that's the top. And the bottom is just divide by 2. And divide by 2. Now, what I'm going to do, you can do this on a regular calculator as well. I'm going to convert that to a fraction. Most calculators have a button to change decimal to fraction. So math, that's how I do it on mine. You probably can't see it. It says 1/12. And that's my final answer. 1/12 of a centimeter per second. So you think, is that a fast speed or a slow speed? That's really slow. The centimeter is like that big. So you're moving 1/12 of that every second. Very slow. All right, so that's converting between angular and linear velocity. So for the test tomorrow, so again, if you're thinking of making a reference sheet, which is optional, but if you want one, you can have it. These are the topics you would want to play. Okay, distance formula. Have a couple problems with that. Midpoint formula. Couple questions on that. Converting from degrees to radians. And radians to degrees. Okay, both. For this one, I'm going to look for exact answers and decimal. So there might be some where I say, go ahead and round it off to 2 decimal places. Some where I say, just leave it exact. What else did we do? Arc length. Area of a sector. And the last thing we did, that was today, angular velocity. So those are the different topics that will be on the test. It'll be a mixture. There'll be some multiple choice, there'll also be some kind of short answer type. And it will be on Edge Elastic. So make sure tomorrow that you come in, your Chromebook is charged. If you don't have a Chromebook charged, unless you can get one from the library, you will not be able to take the test. Yes?
Are you grading it with work as long as you put in a good effort to get it good, or is it from the answers?
For the test?
Yeah.
So for the test, I do grade it in terms of correct. Okay, you have to get it correct to get full credit. You can get partial credit. Most of these problems, I think, are just one step. They're not like word problems that have 2 or 3 parts. So I don't know if any of these would have partial credit, but in general, I do give partial credit. Yes.
All of the names have to be handwritten.
Yes, the reference sheet, well, your notes that you take in class, I'm assuming if you're writing things down, it would always be handwritten. But your reference sheet that you make for the test, yeah, that would be handwritten. Yep, can be double-sided, this side 8.5 by 11 inch. And you can put examples, definitions, formulas, whatever you want to put on that. And I usually collect that after you take the test. Okay, any other questions? And as far as edge elastic, don't be concerned if there's like a technical thing. You're like, I can't figure out where the button is to do this. That kind of thing I would help you with. If you ask me though, am I using the right formula to find the distance? Well, that I can't help you with. I'm checking to see if you know that, okay?